So now, for this is information to online participants that let me see. My good friend Esa sent me a text message that the voice was no good. So now I have a different mic system. I don't know how is the voice. Is it no good or not? But YouTube officer, can you please listen to my streaming a little while to see if this is understandable? I mean, if the voice is, let's say, recognizable. So now is so what is your deputy YouTube officer, or what is your official name?
No, it's perfect. The sound is perfect.
Yeah, but I was asking, like, what is your ranking? Is it your deputy YouTube?
Yeah, definitely.
Oh, okay, good. All right. So now it's perfect. Again, really sorry that I realized this problem too late. Again, the first part of the lecture is no good quality-wise. The second part should be perfect. And is not just that, but even, my ears server is cooperating. So we have everything up and running. So everything looking almost too good. Let's not saying that, because things for sure will go wrong once saying that. Okay, then what I will do is that I will take a look at the so where is my Socrative? Gonna check it out, the Socrative solution. Is this I'll look at that. So Socrative 2 is a no, I don't want to start the new one, but I'm not sure what's the deal with the current Socrative. Don't know how is the solution. I guess that I need to just to take a look. Cannot do that. All right. So at least something is not working correctly. So Socrative is not cooperating. But let me take a look at something else. So I wanted to show you. Here are the few YouTube videos regarding. Okay, not that. Let's use another link. Not that. So there's several links. No, these are not working. Anyway, so the links that are available in my PDF, take a look at them to learn more about the Coriolis acceleration. They are actually very enjoyable videos, so it's highly recommended to take a look at them. Just one more thing that is missing is here my pen. So check this video, check this video, and then there's one more video. This is maybe the best one. I recommend you to get started from this one to learn more about the concept of Coriolis acceleration. But again, we don't have it because we are dealing with rigid bodies, and we have kinematic definition where the vector u bar is constant. That's why we don't have a Coriolis acceleration. What would happen if we are dealing with the flexible bodies, deformable bodies? That's a different story then. Then we would have Coriolis acceleration, because in case of deformable bodies, the vector u bar is no longer constant, but it can change its length because of the body deformation. So then we would have, it is related to kinematics, not rotation of Earth. And you may or may not have it depending on the kinematic notations. Clear? All right, makes sense. So here's finally a picture how these accelerations look like. The first acceleration, which is this translational acceleration, that's simple. It's just the translational acceleration of the body reference coordinate system. But then what about these normal and tangential acceleration? Tangential acceleration is tangential with respect to rotation, and rotation, now very important to understand this. Rotation is measured as orientation of the body reference coordinate system. So here the theta is located at. So it's tangential with respect to that. And then the normal acceleration, because it was a minus, the vector here pointed towards the origin of the body reference coordinate system. Those are the three acceleration components. Any comments or questions? By the way, maybe we can set another competition. So the first student that is raising a hand and say, Aki, actually, I don't think that I understand. Can you please repeat? Can you please repeat? We'll get an award. What is an award? I don't know. But something. But it needs to be a real reason. No, it's not good that if you raise your hand right away and say, I don't understand. But you need to explain what exactly you don't understand. I would be very happy to repeat, to look things from the different perspective, because that usually is the one that helps. But you're good? You're comfortable with this? Again. Oh, so we have a winner in a competition. Yes. Angular acceleration, this one? Oh, okay, so where is that? All right, so we have a winner in a competition, so it should be this one. But it's not. It's the same vector, that is just differentiated with respect to time. So it's physically, so your question is where that is physically located at. It's located at this point. It's this same thing, except that this is, if we have a position, the velocity of that vector measures its change, and acceleration measures the change of the velocity. But it still is, if you look at physically where that is located at, it is measuring from the origin of one coordinate system to origin of another coordinate system. Beautiful question. 2 points, whatever that may be. Anything else? Tangential acceleration. Tangential acceleration is perpendicular. If you look at, if I have here vector u bar, it is perpendicular with respect to vector u bar. Perpendicular. Why? Because I'm measuring this rotation with respect to body reference coordinate system. That's how it goes, even though that the body may be connected to ground from the revolute joint that is located here. That doesn't matter. That doesn't matter because to measure kinematics, this is what we said already. It is theta. And we are looking at that with respect to body reference coordinate system. It is a little bit of concept that if thinking that heavily, you can get the headache. But that's how it goes. U-bar, vector U-bar. Vector U-bar, again, what's the role of vector U-bar? It is defining each one of the particles within the body. Now what that is then, it's like if you look at, because in this particular examples, I'm looking at the acceleration of one single particle. Then I have many particles, infinite number of particles within the boundaries of the body. But yes, it is takes a little while to think about it. Another thing that takes a little while to think about it is this coordinate system. How they go, like if you really wanted to rotate it. And that's, by the way, this comes back to this gang sign. Remember I said that if we see in a corridor, you don't say hello Aki like this, but you say like respect. This is, because we are not thinking anything else except coordinate systems. So it's like respect. Can you please do it for me? Nice. Maybe it should be like here, like close to your heart. I don't know. This is enough. Okay, so that's a gang sign. So only that's the gang. So you cannot use it in any other purposes. And I got the message. Is this Esa again? That this is now much better voice. Thank you, Esa. All right, so now something that is very, very, very important to learn, and that is generalized coordinates. Because now we have the kinematics, but what then? What is that we can do with the kinematics, and what is that we can do with this equation that we are repeating over and over again? Well, there is something very important to understand. We have to look at what are the variables in this equation. And once we are able to identify the variables, those are the ones that will be used to express the equation of motion. Because we have to solve the variables of the system in order to understand its configuration at any given time. So what are the variables? Those are the ones that will be called as a tenorized coordinates. So those are something that we will build the equation of motion and solve the tenorized coordinates. And again, those are the variables, those are the items that will change when body will translate and rotate. So that's the concept of tenorized coordinates. All right, without further ado, let's take a look. So again, I have this planet body, this potato-shaped body here. And in my potato-shaped body, I want to describe one random arbitrary particle. Particle is called P here. How that will happen? Well, again, I will repeat the equation that I'm already very much familiar with. So I'm first describing the translation of the body reference coordinate system, and then I will account the orientation of the body reference coordinate system. That will be handled by this 2x2 rotation matrix. And then finally, I'm going to travel to location of the particle with help of vector u-bar. All right. Now, what we need to do is that we need to identify what are the variables, what are the changing components in this equation. Now, first of all, how is that they can change? Well, if I translate the body, if I move then along the global x or along the global y-axis, what will happen? Well, this guy, this translational guy, it will recognize the motion. It will measure the translation because its numbers start to change if I'm moving the body along the global x-axis. Remember how this looked like? You know, the vector r consists of two components that are rx and ry, because this vector here have two components, projections in x and y direction. Clear? So now if I'm going to move it along the global x direction, this component started to recognize that it's going to change its values all the time. Well, if I'm going to move it then in the y direction, this will recognize that change. What if I'm going to rotate my body? Then this will recognize that. So what about vector u-bar? If I'm going to do like this, how the vector u-bar will recognize it? What? Even if I do like this? Yeah. Still? You're right about that. It is always constant. Even if you do like this, or if whatever you're doing is always constant. I was just trying to make you feel confused. Almost made it. Almost. So, okay. So it's always constant. No matter if you do it like this or that, it's always constant. So it's not a variable. All right? So now, if I make a list of tenorized coordinates, if I have a system of one body, what are the tenorized coordinates? Rx, Ry, and angle theta. That's it. Nothing else. Nothing else. Because vector u-bar is not the variable because it's a constant. It's not used to measure anything. I mean, it is of course used to measure the position with respect to body coordinate system, but now I'm looking the things with respect to global coordinate system and when things are moving. What are the variables that are recognizing the motion? And what are the variables that are changing when the body is translating and rotating? So that's it. 3 variables. When I'm forming the vector based on these variables, this vector is denoted as a Q and is called tenorized coordinates. So why this is important then? Because next we're going to start solving the tenorized coordinates first by using kinematics. So we're going to solve, everything that we know about the system, and then we're going to solve the tenorized coordinates. because we have to know them. If we don't know the generalized coordinates, we cannot solve the responses. It's simple like that. So it's a bit confusing because we started from this kinematics, and now we are looking the variables that are in a kinematics. But that's how it is. Then later, we're going to use these variables to express all the forces. So all the forces will be converted to be expressed by using generalized coordinates. Are you still doing like, yeah, I'm sure you do that, and you're thinking like, okay, so it's still 30 minutes and then I'm off. Friday I'm gonna go to have a drink with my friends, and then it's a weekend. That's all right, because you can later watch the recording, so it's all right. Okay, clear? Kind of. All right. So this is shortly about how is the things in a three-dimensional space. Not so important, but just for your information, in three-dimensional space, one body needs 6 or 7 generalized coordinates. By the way, the one thing that I forget to mention when I explained about these quaternions, the ones that are based on 4 parameters to describe the rotations. Obviously, even if you use 4 parameters, body can still rotate in 3 different ways. How is that you can fix this problem if you have 3 different ways that the body can rotate and 4 variables? Well, you introduce the one constraint such the way that there's only 3 independent rotational parameters. But you don't need to worry about that. It's something that if you want to get the doctor degree under my supervision, oh, definitely, then you need to know this back and forth. Even if I go and woke you up during the night, you need to know this. But now you don't. All right. Okay, so that's about it. Now, one more thing that is important. What if you have 2 bodies? How many generalized coordinates you need then? And we are looking at planar case. Then you need how many coordinates? Let's set the vote. 1, 3, 6, 9, 100. Who is voting for 1? No one? 3? And again, we have system that consists of 2 bodies. So someone is voting for 3, 6. No one? No, a few. 9? 100? More the better? No? Correct answer is 6. 6. Because first body needs 3 coordinates. Second body needs 3 coordinates. Third body needs, correct, 3 coordinates. Fourth body needs 3 coordinates. Everybody needs 3 coordinates. Oh, look at that. Everybody needs 3 coordinates. That's almost like a song. Yeah, okay, so it sounds good. So each body is 3 coordinates. Now if you have 100 bodies, how many coordinates? 300. So that's always what is needed, because we are not looking the motion limitation here. We're just looking how many coordinates we need. That's it. Later, we start to eliminate the coordinates. Actually, we don't eliminate the coordinates later, but we are looking the ways how the motion can be limited, but not yet. All right, clear. All right, so then if I have a body 1, just the one body, what is the correct number of generalized, what is the correct list of generalized coordinates? Let me put the Socrative on. So you can read the options here. So the options are available here. I just need to look at what is the deal with the Socrative. So is I guess that there's only way that I just need to close the current one and launch the new one. The problem is that the internet connection here is no, forget about that. So we are not looking that. In body A, generalized coordinates are now the options. To see the options, these are the options. Only one is correct. Only one is correct. Maybe what is the best way to start looking this? My recommendation is that look at the number. How many numbers we need? So how many we need actually? Because everybody needs 3. Remember that song? So that leaves us what? 2 options. What are the variables? What are the components that are changing? You guys done? Can we move on? What's the success rate this time? 95? Seriously? Remember, but you have to consider this. You know, last time I was saying, don't say that the body can rotate. Don't say, please don't say. And you saw that it was still there. So it can happen. And why it can happen? Well, the reason is obvious, because you don't listen to me, but you're thinking this story is like, I'm gonna, on a Friday I do this, Saturday I will be very, very busy, and then, oh, in-class quiz. What is this? Okay, rotational particle. That's how it goes. I've been there, so I know how is your reasoning. I know how is your thinking goes. All right, so I'm gonna move on. I'm gonna leave this on for a little while, because then there is something that is very, very, very important to learn. What's that? Constraints. Because now we know how the body can be described. We know what are the variables, but we do not know how to introduce these motion limitations that are called constraints. We do not know how we can introduce joints between the bodies. But we have the ingredients to make it happen. What are the ingredients that we can make this happen? Surprising enough, it's this equation. We're just going to use this equation. That's it. And that is the one that will limit the motion possibilities. You may be like, really? Can you really do it with that equation? Yes, you can. Yes, you can. And actually, it is very simple to do so. So let's take a look at that. So what follows is a little bit of mathematical definition, this and that. We need to take a look at what is the definition of this degrees of freedom. And then we're going to look at the example. And once you look at the example, all becomes clear to you. So it's like, yes, that's what I've been always thinking in my life. Now it's clear. All right, so constraint equations. This is the first very important consideration. Remember that in case of 1, 2, 3 moving bodies, how many generics we have to use to describe this system? Please, how many? How many generalized coordinates? So if we have 1, 2, 3 moving bodies, how many generalized coordinates we need to describe this system? Yes, that's 9. So we need 9 generalized coordinates. 9 generalized coordinates. What are these generalized coordinates? Well, you know, they are Rx associated to first body, Ry associated to first body, theta associated to first body, Rx associated to second body, Ry associated to second body, theta associated to second body, and then the third body. I'm running out of this space. So, but you got the concept. You understand how it goes. Those are the 9 coordinates. Now, these coordinates cannot change as they want. They cannot, because the system is constrained. And it is constrained because of the revolute joint that is here, 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 and then the translational joint that is here. So, it's not possible to take one random generalized coordinate, just say this one, and to say, go ahead and move as you want, because it cannot. What that would mean that I will take this crankshaft and move the crankshaft here. If I do so, you know, I will violate against the constraints, because the constraints are saying you cannot move as you want, but you're limited. You have to follow you have to move in a certain way. What is this way? Well, if you take a hold of, say, piston body and move that back and forth, you will see that the other bodies will follow certain way because of the constraints. How many different ways system can move? That is called degrees of freedom. Number of degrees of freedom. How you can compute that? Well, you need to have two pieces of information. First of all, you have to know how many generalized coordinates you have in total. And then you have to compute how many constraint equations you have. You don't know the constraint equations yet. We will get back to that. But already for your information, to describe translational joint, you need two constraint equations. I have here 1, 2, 3 rotational joints, and then I have one translational joint that too needs two constraint equations. So I have 8 constraint equations. 9 minus 8 is 1. So this system has a 1 degrees of freedom. So it can move only one way. And the one way is the piston goes back and forth, crankshaft and connection rod are following because of the constraints. Now we just need to learn how we can introduce this mathematically. More painful stuff. So this is how it looks mathematically. So we have here vector of generalized coordinates that consist of or is defined by number of bodies. And then we have number of constraint equations. And this constraint equation, you can put it in a form of a vector. A vector has certain number of components. How many? Well, that depends on your case. But constraints are a function of generalized coordinates typically, and possibly time, possibly. We will take a look at these names and definitions a bit later, but when you look at the details of this vector, constraint vector, it consists of 1, 2, NC number of constraints, independent constraints. Okay? I have here n number of generalized coordinates, so the number of degrees of freedom can be calculated simply such the way that is n minus nc. You look at how many components you have in the generalized coordinates, how many components you have here in constraint equations. That's it. Clear. Let's look at an example. Let's look in details. How is it we can introduce this magic motion limitations, these constraints, these joints between the bodies? Easiest ways is just to get started. So let's take an example. So I have here 2 potato-shaped bodies, not 1 but 2. What I would like to do here is that I would like to limit the motion possibilities of these 2 potato-shaped bodies in such the way that I will introduce a revolute joint that connects these 2 bodies together. How can I express this revolute joint mathematically? Well, actually, like I said, it is very straightforward if we just use this kinematic notation that we're used to deal with. Okay, so let's look at the situation. So here is how it looks. So I have here a body that is called A. All right, and then I have another body that is called B. Here's a B. And then I have point where the revolute joint is located at. And that location is called O. All right? Each bodies, they all both have a body reference coordinate system. Because this is the way we're going to describe the kinematics based on the body reference coordinate system. So where they are located at, that doesn't make any difference. They could be located at wherever you want. Okay, here in this particular example, body reference coordinate system of body A is located in this corner, or this particular location. Okay? What about the body B? It is located in this particular location. How we can define the revolute joint? Well, first of all, we have to understand the nature of revolute joint. Revolute joint means that, you know, is sharing the point between two bodies. Let's say that, I don't know how it is streaming, but if I have a pen body, stick body, and if I put them together with help of revolute joint, it means that they will stay together like here. They can rotate like this, they can translate like this, they can translate like this, they can rotate like this, but they no longer can separate like this because revolute joint is located here. So it's not allowing them to separate it. This meaning that this point and this point, when expressing in a global coordinate system, they must have the same value. How we can make that happen? Well, we already know that because remember this magic equation we are dealing with? Translation plus orientation, that's the magic equation. So we're gonna just go ahead and express the location O first by using the body A. So we're first gonna translate the origin of the body reference coordinate system. Then we're gonna count orientation of the body reference coordinate system. How we can do that? Again, with help of rotation matrix. And then we're gonna take the vector U bar to trouble that particular location where the joint is located at. Make sense? Okay. We go here. So we end up to be here. Now we're here. Now we're gonna redo it, but this time we're gonna travel first to body reference coordinate system of body B. We're gonna count the orientation of body B. This is translation, this is orientation. And then we're gonna travel to point O with help of vector U bar. And then we're gonna say that these two notations must be equal. End of the story. That's it. So that's a revolute joint. So let's look at the details, how it looked mathematically. Okay, so I have here translation of body reference coordinate system A, rotation of first body, and vector U bar, and then the same thing except this time with respect to body B. Translation, rotation, and vector U bar. Now I'm just gonna go and do the mathematics. What is that? Well, I have to multiply the rotation matrix with corresponding vector U bar vector. And once I do that, I'm gonna move all the components to the left-hand side of the equation. Okay, so once I do that, this is how it looks. And now what is left in the left-hand side of the equation is 0. I will do the same for this, and it's 0. I have two independent constraint equations that physically means that there is a revolute joint that connects these two potato-shaped bodies together. Here's a question for you. How many degrees of freedom this system has? Yeah, that's a question. It's a bit complicated, but still gonna ask. 6, 4. Anything else? 1, like in a case of this crankshaft mechanism. Should we vote it again? Let's vote. 1. The option are 1, 2, 2, then 4, 6, and 100. Who is voting for 1? Seriously? 1. There's 1. Okay, then who is saying 2 degrees of freedom? How many different ways the system can move? No 2? Who is saying 4? Almost. Oh, okay, so it seems that most of you are saying 4. Who is saying 6? No one. 100? No one. You know, the correct answer is what? 4. Correct. Is 4. How can I know it? Well, easiest, well, I don't know if this is easiest, but the mathematical way to say it is that I first take a look how many generalized coordinates I have. So how many generalized coordinates I have? 6. 6. how many constraint equations I have? 2. Gives me 4. So what are these 4 degrees of freedom? It meaning that the system can move in 4 different ways. Here's the first way, translation along the global x-axis. Here's the second way, translation along the global y-axis. Then rotation like this. And then the relative rotation. Got it. Easy. Isn't this quite easy? Quite easy. Are we all doing like this? No. Why not? Why not? Challenging. It's like you just need to push yourself. Push it. Remember what's the most important, advice to this course? Can-do attitude. Correct. Can-do attitude. It will happen. First time you hear this stuff, it's like, what? Unbelievable. But you keep on repeating. That's why you need to follow this course all the time. You skip the 1 week, you come back, it's like, oh really? This is coming from the different planet. Because I have some bad news for you guys. Bad news is this. I need to remove all these drawings. If I make a, curve which says like how is a level of difficulty in this course. I have here x-axis which is equal to time. This is first lecture, this is second lecture, so first, second, then the third, fourth, and this is y-axis is level of difficulty. Level of difficulty, LD. How difficult these are things. So we're moving here, so we negative something. So it's not so bad. Then the next week we're coming a bit up here, and then we're gonna go sky high. So it goes all the way up there. I don't know, high up. And then slowly we're coming back here. All right. Good proposal. Very good proposal. Let's put it in a no. It's I will think about it. That's a good one. Okay, so here's how you can compute the number of degrees of freedom. So this is what I just explained to you. So you need to know the number of generalized coordinates, number of constraint equations. And now it's almost 6 o'clock, so we are about to close. But before we're leaving, something that is very difficult to understand. And is this, I have this crankshaft mechanism such the way that is fully described by constraint equation. Fully described. Remember, I originally have 9 generalized coordinates in the system. Okay? So let's put this again here, 9 generalized coordinates. Then I have, because of this revolute joint, because of this translational, revolute joints, and 1 translational joint, I have 8 constraint equations. What I'm doing here, I'm adding 1 more constraint. What is this 1 more constraint? I'm saying that this crankshaft is no longer free to move whatever it wants or rotating however it wants, but it has to follow 1 additional constraint. 1 additional constraint is defined here. It has to follow the angular velocity that is predefined. So it's predefined. What that means? It means I'm adding 1 more constraint. What's this? 0. So I have a system that is kinematically fully defined. Remember, my unknowns are generalized coordinates. And my kind of solution to solve these unknowns are constraint equations. I have 9 constraint equations, 9 unknowns. So that's all the information that I need in order to solve the response of this particular system, because it's kinematically driven. is driven by constraints. Everything is predefined. So I can just use a kinematic analysis. I'm using my vector of constraint equation, that is a function of generalized coordinates and possibly time. I'm going to simply solve this set of nonlinear equations to get generalized coordinates out of it. That's called kinematic analysis. Makes sense? You almost like everyone was doing like this simultaneously. What about this? The same mechanism, but now this 1 degree of freedom is driven by a moment. Conceptually, very different story. Very different story, because I have this 1 degree of freedom. And 1 degree of freedom is actuated by a force or moment. There is no other way to solve the response except write the equation of motion and solve the equation of motion in forward of time. I have to look at the forces. Constraints are not enough to solve the responses. You got it? So I have here, dynamic system. That's what we are going to look a little later. Next week, next Monday, we're going to look at the kinematic system. We're going to solve the kinematics. And only way to solve only way to run the kinematic analysis is that the system must have 0 degrees of freedom. If not, then we cannot solve that by using kinematics. Why not? Because we don't have enough information to do so. We have less constraint versus number of unknowns. That's why. And then there's also a possibility that is over constraint. So there may be, let's say, a revolute joint here that connects the connection rod to ground. What will happen? No motion. We are speaking with rigid bodies. No motion. Okay, confused enough? Is this also singularity? So is it this equal than singularity? There is something to answer your question. There is something that is called redundant constraints. Redundant constraints is a kind of singularity, meaning that all the constraints are not independent, but they are depending on each other. This is simply over constraint, so meaning that there is no motion possibilities whatsoever. It's not the singularity, but this redundant system is very interesting, and we definitely will get back to that on Monday. Here, this is how you can count how many constraints you need in a different planar cases, but it's already more than 6 o'clock. So thank you very much, and good to know that the mic system is finally cooperating. Oh yes, sir. Material on for this lecture. Right, so it's always right after my lecture I'm gonna go and download the material to Moodle, because it's always a bit unclear how much I can explain to you within 2 hours. So that's why it's not also another reason is that I don't want to solve the questions related to these in-class quizzes to you. Yes. I will explain the solution one more time to you on Monday. Okay, how is a success rate here? We have only 4 students that I answer. Are you guys giving up? How come? Is something wrong? Can you please double check this in-class quiz, and what was the question? Question was this one. So something went wrong. Okay. I need to check, like, is it still coming? No, it's kind of like, All right, I'm gonna just show like what was the final result. Half and half, 50%. So it could be better than that. I'm gonna get the results. You know, the results are, I think they're coming to my inbox, my emails later. But you know, this is definitely incorrect. Why? 2 components. Everybody needs 3. Everybody needs 3. So it only leaves this and this. And this is full of vector U bar. So no good, absolutely no good. So the correct one is this. Okay, so thank you very much and see you on Monday.